Okay, let's talk about acid-base reactions. These are also called neutralization reactions. We learned how to name and write formulas for acids. These are the characteristics of acids. Acids form hydrogen ions in solution. We can recognize them because the formulas start with H. The names are even easier because they actually have the word acid in the name. I mean, how easy is that? Acids taste sour, and they can dissolve some metals. So like Sour Patch Kids and all those sour candies that my kids love so much, the thing that makes them sour is acid. Bases tend to form hydroxide ions in solution. And what I want you to recognize as a base is any metal hydroxide. So sodium hydroxide, lithium hydroxide. It's a metal with hydroxide. You should recognize that as a base. Bases taste bitter, and they feel slippery. So if you get sodium hydroxide on your hands in lab, it'll feel slippery. And that means you need to wash it off right away before it dissolves your skin. Bases are a lot more dangerous than acids are. Here are some common acids and bases. Hydrochloric acid, hydrobromic acid, nitric, sulfuric, perchloric, and acetic. These are ones that might actually encounter in the lab. And here are some bases. Again, they're all metals with hydroxides. They're going to be the more soluble ones because if it's insoluble, it's not as useful as a base, but it can still function as a base. So in an acid-base reaction, we have an acid reacting with a base. And it's called neutralization because the acid and the base neutralize each other. What forms is water and a salt. Salt is a generic term for an ionic compound. So in everyday life, when you say salt, you mean sodium chloride. In chemistry, we just mean any ionic compound. So potassium chloride, lithium acetate, those are all salts. So here we have an acid, hydrochloric acid, reacting with a base, sodium hydroxide, and the products are water and salt. Every time I say a salt, I think of this picture. This is a salt rifle. You guys are just so boring. Okay, so the pattern of the reaction is acid plus base yields water and salt. And what we'll see is the net ionic equation for many of these reactions ends up being exactly the same. Hydrogen ion from the acid with hydroxide ion from the base forming water. The salt here is usually soluble, and so the other ions that were with the hydrogen and the hydroxide just remain in solution as spectator ions. So let's look at how this works. We're asked to write a molecular and a net ionic equation for the reaction that occurs between aqueous H2SO4 and aqueous KOH. That's sulfuric acid and potassium hydroxide. So the reactants, you've got H2SO4. It's aqueous. And we've got potassium hydroxide. It's aqueous. This is an acid, it starts with H. This is a base, it's a metal with hydroxide. Acid plus base gives salt and water. But let's look at what happens. We can actually approach this just like we did the precipitation reactions by thinking about ions changing partners. So we can break sulfuric acid into ions. It's going to be a hydrogen ion and sulfate ion. We know that the charge on sulfate is 2 minus because we memorize it. You can also figure it out from this formula because hydrogen is in group 1 and it forms a +1 ion just like the metals. And then potassium hydroxide, we've got potassium ion and hydroxide ion. And we're going to swap partners. So we're going to put hydrogen ion with hydroxide ion. And we're going to put potassium with sulfate. The potassium has to come before the sulfate, because it's Mr. and Mrs. Potassium ion and sulfate ion. Positive charged ion is always first, because we decided to do it that way. So maybe you're not, really thinking too clearly, and you're just kind of going along, and so you see plus and minus, and you say, oh, well, I just need one of each of those, and I'm going to put them together, and I've got that. And hopefully that looks a little funny to you. Does that look weird? Huh. Well, what if we put the two H's together? What would we have? We'd have H2O. So that's H2O. Oh. Hydrogen ion and hydroxide ion, when they meet up together, they form water. What's the state of water at room temperature? It's a liquid. It's silly to say that this is aqueous, because aqueous means dissolved in water, and how can you dissolve water in water? Right? It is water. Then this one over here, we've got K plus and SO4, 2 minus, so we may need K2 SO4. Is that soluble? Well, you go through the rules. The first line, potassium compounds are soluble. So yes, this is aqueous. And then we need to balance the equation. So you'll notice we've got oxygens everywhere. Let's start with potassium, perhaps, because it's unusual here. So here I've got potassium, and here I've got potassium. So there's 2 of them here, and there's only 1 there. Let's put a 2 over there. I need a plus in here as well. And then let's look at the sulfur. Here I've got SO4 as a unit, and here I have SO4 as a unit. You can balance those as a unit, but if it bothers you that there's other oxygens around, you can do that separately as well. But the sulfurs, 1 sulfur, 1 sulfur, so that's okay. Now we have to deal with the rest of this mess. Here we've got 2 hydrogens and 2 hydrogens. And over here I only have 2. So I need 4. So I put a 2 there. And we'll keep our fingers crossed. Oxygens, I've got 2 oxygens there. And if you want to count them separately, I've got 4 here. So that's a total of 6. And I've got 4 plus 2 is 6. Phew. Okay, so there's my balanced chemical equation. This is the molecular equation. That's the molecular equation. Any questions about that one? It's the same idea of separating into the ions, switching the partners, putting them back together. It's just that one of them is going to end up being water for an acid-base reaction. Now, it also asks for a net ionic equation. So we kind of have things written out here. We just need to edit this a little bit. So net ionic equation, you really kind of need a complete ionic equation first. So anything that says AQ, you're going to separate into ions. So here I've got AQ. So this is going to get separated into ions. It's going to have 2 hydrogen ions and 1 sulfate ion from this guy up here. Okay? This is aqueous. It separates into ions. I have 2 of these units, so I get 2 potassium ions and 2 hydroxide ions. And that's going to make, this is a liquid. Do I separate that into ions? No. So I'm not going to write it like that. I'm just going to copy it down like that. And then this one's aqueous. This is going to give me 2 potassium ions and 1 sulfate ion. So 2 potassiums and 1 sulfate. And this is scribbly messy here because it doesn't ask me to write it out. it doesn't ask me to do a complete ionic equation. It just wants the net ionic equation. But I'm writing this out so that I can see what the spectators are. What are my spectator ions? The same on both sides of the arrow. Sulfate. So I have a sulfate here and I have a sulfate there, so I'm going to cross those off. Sulfate did not participate, it just watched. What's the other one? Potassium. I've got 2 potassium ions and 2 potassium ions. They were just hanging out and watching what was going on. So then I'm going to copy down what's left. Actually, I think I'll do green. So 2 hydrogen ions and 2 hydroxide ions. That's all that's left on the left side, and on the right side, 2 water molecules, liquid. So this is going to be the net ionic equation. But what's not quite right about this one? All the 2's, right? Those 2 coefficients. So I'm going to get rid of those. So I'm going to erase that one, and erase this one, and erase that one. I divided everything by 2. It's still balanced. I have a total of 2 hydrogens and 1 oxygen on this side, 2 hydrogens, 1 oxygen on that side. Any questions?
As far as the test, you would want the simplified one?
I do want the simplified one, yeah. I won't really set out to trick you, but the question may try to trick you. And so what you need to remember on a multiple choice test is you need to choose the best answer. So if it gave you this equation and the one with the 2's in front of it, this one is better. I won't intentionally put one of those on there, but it might slip in. Okay, gas evolution reactions. These are reactions that form a gas as a product. Some of them form that gas directly. When you mix sulfuric acid with lithium sulfide, you can do the same thing here with swapping the partners. You end up with hydrogen sulfide gas. And then the other product is lithium sulfate. Now, how do you know that that's a gas? Well, I wouldn't expect you to know that that's a gas. But if I showed you this equation, you should be able to tell me, yeah, that's a gas evolution reaction. There weren't any gases over here, and now there is. A gas has evolved. A gas has been formed. Other reactions form an intermediate product that's unstable and decomposes into a gas and something else. And that's the case when you mix hydrochloric acid and sodium hydrogen bicarbonate. It forms carbonic acid and sodium chloride. Well, carbonic acid isn't stable. It decomposes. It decomposes and forms water and carbon dioxide. Yes?
May I ask, why does that one look like the acid base?
Why does it look like the acid base? You mean this one?
Mm-hmm.
Well, because this one's an acid. But we can see that it's not an acid-base reaction because this is not a base. It's not. If it was lithium hydroxide, it would be. And it's forming H2S instead of H2O. So we see that this is a little bit like H2O. Sulfur and oxygen are in the same family in the periodic table, and so they tend to do similar things. But it's not an acid-base reaction. This actually is an acid-base reaction. I wouldn't necessarily expect you to know that, but here we have an acid. This is a base, but not the type that I've told you need to know about. Over here we get water and salt. It's also a gas evolution reaction. So some of these reactions can be named as more than one type of reaction. Just like cars, okay? There are lots of things in everyday life. So you can say, well, yes, that Toyota Sienna, it's a minivan. It's a Toyota. It is a gold vehicle. right? It's a four-wheeled vehicle. I mean, you can put it in lots of different categories. Does that mean it's multiple vans? No, it's the same van. We have different ways of describing it. So this is an acid-base reaction. It's also a gas evolution reaction.
Classified as a gas.
This would be a gas evolution reaction because it's forming a gas. It is also an acid-base, but I wouldn't expect you to identify this as an acid-base because the bases I want you to know are metal hydroxides. There are lots of other things that act as bases, but at this level, you don't need to recognize them. So these are the things that form gas evolution reactions. And this is just 4 things you just need to remember. So the first one, if you swap the partners and you get a product that's H2S, it's a gas. You just have to remember it. Sorry. If you swap the partners and you get one of these guys, H2CO3, H2SO3, or NH4OH. So this is carbonic acid, this is sulfurous acid, and this is ammonium hydroxide. These are all going to decompose. Predicting how they decompose really isn't that bad because they all follow a pattern. They all liberate one molecule of water. So let's look at how that happens. So H2CO3. You just need to remember that this is going to decompose and form a gas. Put it on flashcards. When these decompose, water, H2O, is one of the products. The other product you can figure out by just subtracting 2 hydrogens and 1 oxygen from this. So take off the 2 hydrogens and take off 1 of the oxygens. What's left? CO2. That's the gas. Water would be the liquid. So with H2SO3, it's going to decompose into water and what is left. So again, we're going to cross off the 2 hydrogens. We're going to get rid of 1 of the oxygens. SO2 is what's left. That's the gas. NH4, same thing. NH4OH. We're going to take H2O out of it. So there's 1 hydrogen, and then we'll get rid of this one. And then we get rid of the oxygen. We've taken off 2 hydrogens and 1 oxygen from this formula. What's left? NH3. And that's the gas. So there's some memorization here, but it's not that complicated. You memorize H2S is a gas. H2CO3, H2SO3, NH4OH. Those decompose and form a gas. You don't need to remember what it is. Just take H2O out of it, write down what's left, and that's your gas. Okay? This is something that if you're aspiring to get an A, you should learn. If you're just trying to get through and pass, spend your time on more important things. This is not a critical part of chemistry. Okay? So writing equations for these guys. It starts off the same. Write a skeleton equation with reactants and products, and then for the products, you just swap partners like we've been doing, but you have to recognize these guys, that those decompose, and then you also have to recognize that H2S is a gas, and then you balance the equation. So let's do an example. Write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. So hydrobromic acid, HBr. So the prefix hydro tells me this is not an oxyacid. So it's bromine and hydrogen. And I know that bromine, when it forms an ion, is -1 and hydrogen is +1. And so that's what helps me write the formula. It says it's aqueous, so I'm going to write AQ. And then aqueous potassium sulfite. So potassium is K+. Sulfite is the light version of sulfate. So it's SO3, same charge. So this is K2, SO3. And that's aqueous. We're going to swap partners and see what happens. KBr and HSO3. So K plus and Br minus, H plus and SO3, 2 minus. So I put those two together, KBr. I check the solubility rules. That one's soluble. Potassium compounds are always soluble. And then when I put H2SO3 together, H plus and SO3, I get H2SO3. And then a little light should go off and say, oh, that's one of those. It decomposes, it forms water, and what's left? So I'm going to have water, H2O, and so I'm going to erase the hydrogens, and I'm going to take away one of the oxygens, SO2. I'm going to move that over because I didn't plan ahead very well. H2O is liquid. This is the gas. Okay, so yes, it forms this, the sulfurous acid, and that's aqueous, but it's unstable. So it forms, and as it forms, then it falls apart. Is that what you're asking? This is unstable. So it eventually, fairly quickly, will form this sulfur dioxide and water. And so then we need to look at this and balance it. Let's just try doing it from the beginning. Hydrogen, I've got one hydrogen here and I've got two hydrogens there. So I need to put a 2 on the HBr. Now let's look at bromine. So I've got 2 bromines here and I've got 1 there. So I need to put a 2 in front of the KBr. Here I have 2 potassiums and here I have 2 potassiums, so that's okay. Notice in this equation, the sulfite, SO3, doesn't stay together. It came apart. So I have to balance the sulfurs and oxygens separately. Here I have 1 sulfur and 1 sulfur. I have a total of 3 oxygens. I have 2 plus 1, 3 oxygen. So there's my molecular equation. Any questions? My husband likes to do mental math, but he says it out loud. And he does it differently than I do it. Actually, I usually just whip out my phone and use the calculator. He's always right, but he is just this challenge to himself. But if I try to listen to what he's saying, I get lost because that's not how I think about it. I think that happens with balancing equations too. You can watch me do it, but because you're just watching, you're like, I don't know. That's not what I was going to do next. So, that's pretty confusing. And this is where YouTube is really useful. So if this is all just like some craziness to you, go home this afternoon, pull up this video, stop before I start writing anything. Try to do it on your own. Get the reactants in place. And then maybe watch a little bit of the video to make sure that you're on the right track. But get to the final answer, you may come at it a different way, but as long as you come up with this same equation at the end, you're doing it correctly. And so that's probably going to help it make more sense in your brain than just watching me do it. It's like watching someone do a magic trick, right? It looks really easy and magical, right? It's supposed to. My son's been doing magic tricks. I'm like, how the heck? The last time I saw him do one, he surprised himself because he thought it wasn't going to work, and it did. And he was just like, oh my goodness. So he amazed himself. But you watch someone and you're like, I don't know what they're doing. If they explain it to you, though, and you watch it and you try to do it yourself, then it's like, oh, I see what's going on here. So that's what you need to do with these.